Some ancient creations should not exist. Across forgotten deserts and sunken coastlines, monuments stand that challenge everything we assume about the past. These are not just old stones, they are riddles carved in granite and bronze. This journey explores 30 specific engineering feats from antiquity, structures and devices so advanced in their methods, precision, or sheer scale, that modern engineers still struggle to understand how they were built with the tools of their time. By the end, you will see history not as a linear march of progress, but as a landscape dotted with peaks of knowledge that were somehow reached and then lost. How did a civilization without computers chart the stars with a bronze gearbox? What secret recipe turns concrete into a self-healing material stronger after 2,000 years? The answers are not simple, and that is the point. Each mystery reveals a flicker of genius in the dark, a testament to a forgotten way of thinking and building. What does it say about us that we can send probes to other planets, but cannot replicate the work of hands that shaped stone millennia ago? Our first stop is a structure so immense it was the tallest building on Earth for nearly 4,000 years. The Great Pyramid of Giza is a mountain of mathematics made solid. Its base is a near-perfect square, with sides aligned to the cardinal points with an accuracy within a fraction of a degree. To achieve this, its builders did not have magnetic compasses. They oriented this colossal mass over 13 acres at its base to true north by observing the stars. That is a surveyor's feat of staggering patience and skill, setting the stage for the precision found everywhere within. That precision extends to the over 2 million individual blocks of limestone and granite, some weighing more than 70 tons. These stones were not simply piled up, they were cut, transported from quarries miles away, and lifted to dizzying heights, all fitted together with joints so tight a credit card cannot slip between them. The logistics are the central, unresolved puzzle. How do you organize a workforce to achieve this? How do you move a 70-ton granite slab, intended for the king's chamber, hundreds of miles up the Nile, and then position it perfectly inside a pyramid already mostly built? The traditional image of thousands of laborers dragging stones on sledges is compelling, but it leaves critical gaps in the engineering story. The coordination required, the food and water for a permanent workforce, the management of such a project over decades, all without a written plan as we understand it, suggests a level of administrative and technical genius we are still piecing together. This is why modern replication with only period-appropriate technology remains a profound challenge. We could build a pyramid-shaped structure of similar size today, of course, using steel cranes and GPS-guided machinery. But to do it the way they did, to solve the 1,000 practical problems of quarrying, transport, and assembly with only copper tools, wooden sledges, and rope, that is the real test. It forces us to ask not just how they lifted the stones, but how they thought. What system of knowledge, now lost to time, allowed them to conceive and execute a project of such flawless, enduring geometry? The pyramid is not just a tomb. It is a frozen moment of a civilization's highest capability, a benchmark against which we still measure our own understanding of the ancient world. Yet within that same stone age of engineering, another civilization was thinking not in mountains, but in microscopic detail. In 1901, sponge divers off the coast of a Greek island called Antikythera stumbled upon a shipwreck from the 1st century before the Common Era. Among the bronze statues and pottery, they recovered a lump of corroded bronze and wood that seemed unremarkable. It was only decades later, as researchers carefully cleaned it, that the truth emerged. This was not a statue fragment, it was a machine, a clockwork device of staggering complexity, now known as the Antikythera Mechanism. It is often called the world's first analog computer, and for good reason. Through painstaking analysis using modern X-ray and imaging technology, we now understand it was a hand-cranked device containing at least 30 interlocking bronze gears, housed in a wooden case no larger than a shoebox. Its purpose was to model the cosmos. By turning a handle, an ancient user could predict the positions of the sun, the moon, and likely the 5 known planets across the zodiac. It could forecast lunar and solar eclipses, and even account for the moon's irregular orbit through a brilliant system of offset gears. This was a portable, mechanical representation of astronomical knowledge, a physical embodiment of mathematical theories about how the heavens move. The challenge of replication lies not in understanding the math, which we can now decipher, but in the physical making of it. To build a working replica with the tools of 2,000 years ago is a task of almost unimaginable craftsmanship. Each bronze gear had to be cast, then hand-filed to teeth of precise size and angle, some thinner than a millimeter. These gears then meshed within a cramped space, turning on axles that had to be perfectly aligned. The metallurgy itself is a puzzle, requiring a specific alloy that was both strong and resistant to wear. How did an artisan without precision lathes or micrometers achieve such miniaturized perfection? And perhaps the most haunting question of all, if this one device survived by pure chance at the bottom of the sea, how many others like it were made, used, and ultimately lost? The Antikythera Mechanism suggests a whole school of precision engineering that history forgot, a whisper of a technological path that vanished beneath the waves of time, leaving us to wonder what other gears of genius still lie hidden, waiting to be found. The sea itself is the ultimate test of any material meant to last. While the Great Pyramid stands defiant in the dry desert air, and the Antikythera Mechanism was preserved in the silent dark of the deep, there is another ancient technology that chose to fight the elements head-on. The Romans did not just build for land, they built for the waves, and their secret weapon was a seemingly mundane substance, concrete. But this was not the concrete we know today. Walk along the coast of modern Italy, or visit the submerged ruins of the harbor of Caesarea in Israel, and you will see the evidence. 2,000 years of relentless saltwater, crashing waves, and corrosive tides have done little more than gently wear the surface of these Roman marine structures. In contrast, modern concrete, used in our seawalls and piers, often shows significant deterioration within mere decades. The question is not just what the Romans put in their mix, but why our own, supposedly advanced version fails to match its longevity. Modern Portland cement concrete is a brittle material. When seawater seeps into its pores, it triggers chemical reactions that create expanding crystals, which slowly crack the structure from within. Roman concrete performs in the exact opposite way. Recent scientific analysis has revealed its magic ingredient, a volcanic ash called pozzolana, which the Romans mixed with lime and chunks of rock. When seawater infiltrates this ancient concrete, it does not cause destructive expansion. Instead, it actually activates a slow, ongoing chemical repair process. The water reacts with the lime and the volcanic ash to form new, interlocking mineral crystals that fill the micro-cracks as they form. In essence, the material heals itself. The harbor of Caesarea, a colossal artificial port built to serve King Herod's city, is a monumental testament to this property. Its massive breakwaters, submerged directly into the Mediterranean's punishing surf, have endured for 2 millennia not in spite of the water, but because of it. Every splash and tide contributes to its enduring strength. Decoding the exact recipe and the precise chemical dance that grants this self-healing property has become a major scientific quest. Laboratories around the world are now trying to reverse engineer the Roman formula, not as a historical curiosity, but as a potential blueprint for a more sustainable future. Our modern concrete production is a major source of carbon emissions, and our structures require constant, costly maintenance. the Roman model offers a tantalizing alternative, a material that grows stronger with age and uses less processed fuel in its creation. The challenge lies in the specificity. It is not simply about adding volcanic ash to our mix. It is about replicating the exact crystalline structures that form over centuries, a process we are only beginning to map at the molecular level. This ancient concrete forces us to reconsider a fundamental principle of modern engineering. We often design structures to resist the environment, to be impervious. The Romans, in their wisdom, designed a material that could work with the environment, transforming an apparent agent of decay into a partner in preservation. Their greatest engineering feat may not be a single building, but a recipe written in stone and water, a lesson in resilience we are still struggling to fully learn. While Roman concrete perfected the art of endurance, another ancient culture pursued a different kind of perfection altogether, one of pure, silent geometry. Deep in the jungles of Costa Rica, scattered across former settlements and river deltas, lie hundreds of stone spheres. They range in size from a few inches to over 8 feet in diameter, and some weigh more than 16 tons. They are not rough boulders, but objects of startling precision, carved from hard granite or gabbro by the Dikwis culture, a people who flourished from around 800 to 1500 of the Common Era. The mystery begins with their creation. How do you carve a perfect sphere with surface variations often measured in mere millimeters, using only stone tools? The Dikwis had no metal harder than the rock they were shaping. Researchers believe the process likely involved a technique of controlled fracture. Craftsmen may have first roughly shaped a boulder by heating it with fire and then cooling it rapidly with water, causing layers to crack away. Then, using hammerstones made of an even harder rock, they would have pecked away at the surface, slowly grinding it down toward a spherical form. But achieving true roundness, especially on the largest spheres, would have required constant checking, a relentless process of measurement and correction without the benefit of modern calipers or templates. Some theories suggest they might have used hanging cords to check for high spots, or rolled the spheres in soft clay beds to reveal imperfections. Each method is a testament to an almost obsessive dedication to an ideal form, a pursuit of geometric purity for reasons we can only guess at. This leads to the second layer of the puzzle, their purpose. The spheres were found in groups, often arranged in lines or geometric patterns, some aligned to cardinal points. They have been discovered in what appear to be important public spaces, near the bases of mounds or along pathways. Were they astronomical markers, symbols of power or celestial bodies, territorial borders, or monuments to ancestors? The truth is, with no written records from the Dikwis, their meaning is locked within the stone itself. The final, haunting question is one of movement. Once carved, often at a quarry site, how were these multi-ton granite balls transported through dense jungle and across rivers to their final positions? The most plausible theory involves a system of ropes, log rollers, and immense communal effort, a feat of logistics as impressive as the carving itself. The replication challenge here is multifaceted. It is not just about carving one sphere with primitive tools, a daunting task of patience and skill. It is about replicating the entire cultural and industrial process, the systematic production of dozens, even hundreds, of these objects to a shared standard of excellence. Why invest such staggering effort into creating objects with no apparent utilitarian function? The spheres stand as a silent argument against purely practical interpretations of ancient engineering. They suggest that for some cultures, the drive to impose perfect order on a chaotic world, to create enduring symbols of harmony and balance, was a powerful enough motivation to move mountains, or in this case, to shape them into flawless orbs that still roll silently through the centuries, guarding their secrets in the green heart of the jungle. A perfect sphere represents one kind of mystery, but a simple clay pot can conceal another. In the basement of the National Museum of Iraq in Baghdad sits an artifact that looks utterly unremarkable. It is a small, yellowish clay jar about the size of a man's fist, dating to the Parthian period, roughly 2,000 years ago. Found with a group of other objects in a village near the city, it would have been catalogued and forgotten were it not for its peculiar contents. Inside the jar, researchers found a rolled copper cylinder sealed at the bottom with asphalt, and within that cylinder, an iron rod. The asphalt stopper also served to isolate the iron rod from the copper cylinder, preventing them from touching. To anyone familiar with basic electrical principles, this configuration is instantly recognizable. It is the core components of a simple battery, a galvanic cell. Fill the jar with an acidic or alkaline liquid like vinegar or grape juice, and the electrolyte would allow a chemical reaction between the two dissimilar metals. A voltage difference, a small electric current, would flow between the iron and the copper. This is the heart of the controversy known as the Baghdad Battery. Did ancient Mesopotamian artisans, centuries before the Common Era, stumble upon the principles of electrochemistry? The potential function is where speculation runs wild. Some experiments with replicas have shown that a jar like this could produce a low voltage, around 1 to 2 volts. While not enough to power any device as we understand it, such a current could have subtle, noticeable effects. One prominent theory suggests it could have been used for electroplating, the process of depositing a thin layer of one metal, like gold or silver, onto the surface of another. A small current is all that is needed to initiate this chemical bonding, and the ancient world is full of examples of exquisite gold-plated objects. Could this have been their method, a secret held by guilds of metalsmiths? The debate among historians and archaeologists is fierce and unresolved. Skeptics argue there is no corroborating evidence, no wires, no electroplated artifacts definitively linked to such a device, and no textual references to anything resembling electrical knowledge. They propose alternative, more mundane uses, suggesting the jar could have been a storage container for sacred scrolls, with the iron and copper merely being protective housings. Yet, the design feels too specific to be accidental. The intentional separation of the metals by an asphalt insulator is precisely what a modern engineer would do to prevent a short circuit and preserve the potential difference. The challenge of replication here is not physical but contextual. Building a working model of the Baghdad Battery is trivial for a modern hobbyist. The profound difficulty lies in replicating the thought process, the chain of discovery and application that would have led an ancient artisan to assemble these three common materials in this exact configuration for a purpose we can no longer clearly see. If it was a battery, what was its place in their technological worldview? Was it a revered tool, a curious toy, or a forgotten dead end in a line of inquiry that simply went no further? This humble clay jar forces us to confront the gaps in our historical narrative. It suggests that flashes of insight, understandings of natural phenomena we consider modern, could have flickered into existence and faded away, leaving behind only a cryptic artifact that refuses to give up its secret, a silent vessel that may have once held not vinegar, but the very spark of a lost idea. The pursuit of a forgotten spark leads us to a place where giants walk, or rather, stand in eternal silence. On the most isolated inhabited island on Earth, a speck of volcanic rock in the vast Pacific, stone faces gaze inland with an expression of profound, unreadable calm. These are the Moai of Rapa Nui, Easter Island, and they represent one of archaeology's most captivating logistical nightmares. Nearly 1,000 of these monolithic statues were carved from compressed volcanic ash at a single quarry inside the crater of an extinct volcano. The average Moai stands about 13 feet tall and weighs around 14 tons, but the largest one ever attempted, left unfinished in the quarry, is a colossal 70 feet long and estimated to weigh close to 270 tons. The creation of the statues themselves is a feat of sustained artistry, using only stone hand picks called toki to slowly chip away the soft rock, freeing the forms from the mountainside. But the true, enduring engineering mystery begins after the carving was complete. How did a society with no metal, no wheels, and no large animals for traction transport these multi-ton giants across miles of rugged, undulating terrain to their final ceremonial platforms called ahu, often on the coast? For decades, the dominant theory involved a slow, grinding process of rocking the statues forward on log rollers, a method that would have consumed vast amounts of the island's precious timber. This theory contributed to a popular narrative of ecological collapse, where the islanders deforested their own home to move their gods, a story that carries a heavy, cautionary weight. But recent experiments have challenged this assumption and deepened the mystery. A compelling alternative, supported by local oral tradition and successful small-scale tests, suggests the Moai might have been walked. In this method, teams of ropes are attached to the statue. By carefully pulling one side and then the other in a rhythmic, rocking motion, the statue can be made to pivot on its curved base, effectively waddling forward in a controlled, upright gait. This method uses far less wood, primarily for stabilizing the statue during pauses, and could explain the statue's distinct design, with a forward-leaning center of gravity that aids the walking motion. Yet, even this elegant solution only partially solves the puzzle. Successfully walking a 14-ton stone giant a few hundred yards on flat ground in a controlled experiment is one thing. Replicating the journey of the actual Moai, some of which were moved over 10 miles across broken, rocky landscapes with slopes and obstacles, is an entirely different scale of problem. The coordination required, the risk of a catastrophic fall that would shatter the statue, the sheer physical endurance of the teams, all speak to a society with extraordinary social organization and engineering intuition. The final act, the erection of the Moai onto their ahu platforms, adds another layer of complexity. How do you lift a multi-ton statue and then lower it perfectly onto a stone platform, often after first placing a separate, multi-ton red stone cylinder, a pukao, on its head as a top knot? The likely method involves building a gradually rising stone ramp and using a system of levers and ropes to inch the statue upward, a painstaking process of millimeters per day. Modern attempts to replicate these feats, even with the advantage of modern safety gear and planning, have been fraught with difficulty and near disasters, proving that theoretical knowledge is no substitute for the hard-won, generational skill that the Rapa Nui people clearly possessed. The Moai are not just statues, they are monuments to a specific kind of genius, one that understood balance, momentum, and mass in a profoundly physical way. Their silent presence asks us a humbling question. We can calculate the forces involved, we can propose plausible methods, but could we, with our minds conditioned by machines and computers, ever truly think like the engineers who made these giants walk? The silent giants of Easter Island stand as monuments to what a determined community can move. But what if the ultimate goal was not to move stone, but to define nature itself? Among the 7 wonders of the ancient world, one stands apart as a vision of impossible life. The Hanging Gardens of Babylon are described by ancient historians as a lush, terraced mountain of greenery, a verdant paradise built in the heart of a sun-baked Mesopotamian plain. Classical accounts, written centuries after its supposed construction by King Nebuchadnezzar II for his homesick wife, paint a picture of staggering beauty. Vines and trees cascaded down towering terraces supported by vast stone arches, a multi-leveled garden irrigated by a hidden, ingenious water system that seemed to make the desert bloom. Yet, for all its fame, the Hanging Gardens present a profound historical puzzle. there is not a single piece of direct archaeological evidence, not one definitive inscription or foundation stone found in Babylon that confirms its existence. This absence has led many scholars to question whether the gardens were a real place, or rather a magnificent piece of poetic invention, a traveler's tale that grew in the telling, blending the wonders of other empires into one perfect, imaginary landscape. The debate is fierce and unresolved. Some researchers propose a tantalizing alternative, that the gardens were not in Babylon at all, but in the rival Assyrian capital of Nineveh, built by King Sennacherib a century earlier. Inscriptions there describe a vast, sophisticated irrigation project and a royal garden with water-raising screws, a closer match to the classical descriptions. Whether the gardens were in Babylon, Nineveh, or nowhere at all, the true wonder lies in the engineering problem they represent. To maintain a massive, elevated garden in an arid climate would have required a hydraulic miracle. Water from the nearby Euphrates River would need to be lifted, not just to ground level, but high into the air to reach the uppermost terraces, day after day without fail. Ancient sources mention chains of buckets on a treadmill, or perhaps the earliest use of an Archimedes screw, though that device is dated later. The scale of the pumping operation would have been unprecedented, a constant, energy-intensive cycle to fight evaporation and nourish deep soil beds built on stone structures. The replication challenge is not about proving it could be done, but about doing it with the technology and materials of the era. Could a system of shaduffs, those counterweighted dipping poles, or a human-powered bucket brigade, possibly lift enough water to sustain an entire artificial ecosystem towering above the city? The logistical and physical demands are almost overwhelming to consider. This is why the gardens captivate us. They exist in a space between history and myth. If they were real, they represent a pinnacle of hydrological engineering and a breathtaking display of royal power to reshape the very environment. If they were a legend, they are an even more powerful testament to the ancient imagination, a shared human dream of creating life and beauty in the most unlikely places. The true hanging garden, then, may not be one of soil and vine, but of idea and aspiration, suspended forever between the river and the sky, challenging us to separate the stone from the story. From the imagined garden suspended in myth, we travel to a canvas so vast it can only be seen from the sky. High on the arid plains of southern Peru, the Nazca desert floor holds a secret. Etched into the dark, iron-rich surface are hundreds of geometric lines, trapezoids, and spirals, alongside immense drawings of animals and plants. These are the Nazca Lines, geoglyphs created by removing the darker top layer of pebbles to reveal the lighter sand beneath. They are not mere scratches, but monumental artworks on a scale that defies comprehension from the ground. A hummingbird with a wingspan longer than a commercial jet, a spider over 150 feet long, a monkey with a spiraling tail, all rendered with clean, continuous lines that run perfectly straight for miles across the rugged terrain. The central mystery is one of perspective and precision. The Nazca people created these designs between 500 before the Common Era and 500 of the Common Era, a time when human flight was a fantasy. Without an aerial view to guide them, how did they achieve such accuracy over such enormous distances? How do you draw a perfect triangle with sides over a mile long, or ensure the curve of a pelican's beak is smooth and proportionate when you are standing at ground level, unable to see the whole picture? The likely answer reveals a profound understanding of simple mathematics and meticulous organization. Researchers believe the designers worked from small-scale models, perhaps drawn on pottery or textiles. They could have scaled up these models using a system of stakes and ropes. By establishing a central axis line and using a unit of measurement, teams could plot key points of the design across the desert. Straight lines could be achieved by sighting between two distant stakes, a technique still used in surveying today. For the complex curves of the animal figures, they may have created a series of many small, straight-line segments that, from a great height, blend into a seamless contour. This process would have required extraordinary coordination and planning, a communal project where hundreds of workers, directed by master surveyors, moved across the landscape according to a shared mental blueprint they could never fully witness. This leads to the deeper, enduring question of purpose. Why invest such immense effort into creating art that you yourself could never see? The theories are as varied as the lines themselves. Some suggest they were sacred pathways for ritual processions, walked by priests to communicate with deities in the sky. Others propose they were an astronomical calendar, aligning with solstices or specific star clusters to mark seasons for agriculture. Another compelling idea is that they were related to water, a precious resource in the desert, with the shapes acting as ceremonial markers for underground aquifers. The true function may have been a combination of all these things, a complex language of symbols written on the land itself. The replication challenge here is not about moving massive stones, but about replicating the cognitive leap. It is about thinking in monumental scale while trapped in a human scale perspective. Modern engineers could, of course, use GPS to recreate the lines with perfect accuracy. But to do it the Nazca way, to translate a small drawing into a landscape-sized masterpiece using only stakes, ropes, and shared vision, is a test of a different kind of intelligence. It requires a mind capable of holding a giant image in place while incrementally bringing it to life, one carefully placed stone at a time. The lines are not a message meant for us, but in their silent, sprawling majesty, they communicate something essential about their creators. They tell us of a culture that thought in grand, enduring patterns, that saw the desert not as an empty wasteland, but as a living parchment waiting for a story only the gods, and eventually the airplane, would be able to read in full. While the Nazca Lines required a god's eye view, the Inca built for the gods to touch. High above the ancient capital of Cusco, Peru, the fortress of Sacsayhuamán stands as a testament to a different kind of precision, one not of aerial design, but of an almost supernatural intimacy with stone. Its most famous feature is not a building, but a series of 3 zigzagging defensive walls, built from blocks so colossal they seem to belong to the realm of giants. Some of these limestone boulders weigh over 120 tons, hauled from quarries miles away and up a steep mountainside. Yet the sheer mass of the stones is not the primary mystery, it is what was done with them. The Inca stonemasons did not use simple, rectangular blocks. They employed a technique known as polygonal masonry, carving each irregular, multi-sided boulder into a unique, puzzle-like shape. These giant polygons were then fitted together with such insane precision that the joints between them are virtually invisible. You cannot slip a piece of paper, let alone a blade, between most of these seams. And they achieved this perfection without a single drop of mortar. The walls are dry stone constructions, held together by gravity and geometry alone, a perfect interlocking system that has withstood centuries of earthquakes that have leveled more modern cities all around them. This is where the replication challenge becomes intensely physical for modern engineers and stonemasons. We understand the principle, of course. It is a 3-dimensional jigsaw puzzle on a gargantuan scale. But the how remains elusive. How did the Inca, without iron tools, without the wheel, achieve such flawless fits? The common theory involves a process of trial and error. A stone would be roughly shaped at the quarry, transported to the site, and then placed next to its intended neighbor. Masons would then mark the high points, carve them down, and repeat the process, fitting and refitting, perhaps using a clay or mud impression to map the negative space of the adjoining stone. This incremental process, known as bedding, could explain the perfect seams, but when you consider the scale, the idea becomes almost overwhelming. Imagine the patience and skill required to lower a 100-ton stone, check the fit, hoist it again, shave off a millimeter, and repeat, possibly dozens of times, all using only stone hammers, bronze chisels, and ropes. The logistical and physical demands are staggering. Some researchers propose they might have used a technique involving heated stones to expand and then contract them for a tighter fit, or that they possessed some lost knowledge of sonic resonance to shape rock. While these ideas are speculative, they speak to the depth of the mystery. The walls of Sacsayhuamán do not just defy earthquakes, they defy our assumptions about pre-industrial craftsmanship. They represent a school of engineering where the solution to structural integrity was not found in a binding agent, but in the elimination of space itself. Each stone was persuaded, through unimaginable effort and skill, to embrace its neighbor so completely that the wall became a single, monolithic entity. To stand before these walls is to feel a profound sense of dissonance. The stones are undeniably ancient, weathered by time, yet the craftsmanship feels impossibly advanced, a silent dialogue between human intention and mountain rock that we can still see, but can no longer fully hear. Delhi's humid air should have consumed it centuries ago. Standing in the courtyard of the Qutb Minar complex is a 23-foot-tall iron pillar, weighing over 6 tons, forged around the 4th century of the Common Era. For over 1,600 years, it has endured monsoons, pollution, and the touch of countless hands, yet it refuses to rust. Its surface is smooth, bearing only a dark, protective patina, while modern iron structures around it succumb to orange decay in just a few decades. This is not a matter of luck or a dry climate, it is a triumph of lost metallurgy. The pillar is not made of pure iron, but of a remarkably high-quality wrought iron, forged in a series of small furnaces by skilled smiths. The secret to its longevity lies in what the ancient metalworkers accidentally, or perhaps intentionally, included in its recipe: a high percentage of phosphorus. Modern steel production deliberately removes phosphorus as an impurity because it makes the metal brittle under mechanical stress. But the iron pillar of Delhi was never intended to be a moving part, it was a monumental column. In this static application, the phosphorus played a miraculous role. Over time, it reacted with oxygen and moisture to form a thin, invisible, and incredibly stable layer of iron hydrogen phosphate. This film, only a fraction of a millimeter thick, acts as a self-renewing barrier. When the surface is scratched or weathered, the phosphorus-rich metal beneath simply forms a new protective layer, healing the wound. This phenomenon, known as passive film protection, is a principle modern metallurgists only came to understand in the 20th century. The replication challenge here is profound. We can analyze the pillar's composition and even create a modern alloy that mimics it. But to replicate the entire process, from mining the ore to smelting it in small, charcoal-fired furnaces, and achieving this specific, beneficial impurity profile consistently, is a task that eludes us. It suggests the smiths possessed a deep, experiential knowledge of their materials, a feel for the iron that came from generations of trial and observation. They could not have known the chemistry of phosphorus passive layers, but they clearly recognized that iron made this way from this ore lasted. The pillar stands as a silent monument to an empirical science, a technology born not from theoretical equations, but from the soot and fire of the forge, a testament to the fact that ancient engineers could achieve perfection through practice long before they could explain it through principle. A different kind of glow haunts the stone walls of an Egyptian temple. Within the crypts of the Temple of Hathor at Dendera, a series of intricate bas-reliefs have ignited a modern debate that blurs the line between ancient symbolism and startlingly modern technology. The most famous of these carvings shows a scene that, to a contemporary eye, looks uncannily familiar. A large, elongated object shaped like a modern light bulb or a giant pear is held aloft by a pillar. Inside this bulb-like form, a snake extends in a straight line, its head pointing toward a small box that the pillar rests upon. A figure stands beside this device, as if in an operator's role, while a two-armed jed pillar, a symbol of stability, seems to act as an insulator. To many who see it for the first time, the interpretation is immediate. It looks like an electrical apparatus, a Crookes tube or an early light bulb, complete with a filament represented by the snake and wires connecting to an energy source. This is the so-called Dendera Light, and it has become a cornerstone for theories suggesting the ancient Egyptians possessed, or at least experimented with, some form of electrotechnology. The challenge to modern understanding is not about building a replica, but about deciphering intent. Could this truly be a literal blueprint for a forgotten device, or is it a profound misunderstanding of a rich symbolic language? Mainstream Egyptology offers a compelling, alternative reading rooted in mythology. They interpret the scene not as electrical engineering, but as a depiction of a foundational creation myth. In this view, the bulb is actually a lotus flower from which the sun god emerges at the dawn of creation. The snake is the god Harsomptis, a manifestation of the sun's life-giving power, being born from the lotus and traveling toward the nurturing womb of the sky goddess, represented by the box. The entire tableau is a spiritual allegory for the birth of light and life from the primordial waters, a story carved in stone to be understood by priests, not technicians. The figures around it are deities, not engineers. This symbolic interpretation fits seamlessly within the vast corpus of Egyptian religious art, where objects and animals consistently represent gods, concepts, and cosmic events. The difficulty for the modern mind lies in our own cultural lens. We live in a world illuminated by glass bulbs and powered by invisible currents, so we naturally project that framework onto the past. The carving challenges us to set aside our assumptions and engage with an entirely different worldview, one where light was not a product of tungsten and electricity, but a divine force manifest in stone and story. Yet the mystery retains a tantalizing edge. Even if the carving is purely symbolic, it demonstrates a sophisticated conceptual understanding of light as something that can be contained, directed, and born from a specific process. The precision of the imagery, the clear delineation of components, feels oddly systematic. This is why the Dendera Light continues to captivate. It forces a confrontation between two modes of thought. One sees a sacred metaphor beautifully rendered. The other sees a potential schematic, a ghost of a technology that history forgot. The true feat may not be in the potential existence of an ancient light bulb, but in the carving's enduring power to illuminate a much deeper question. How do we know when we are looking at a lost invention, and when we are simply seeing our own reflection in the polished stone of a distant past? Fire that burns on water is a weapon from myth made terrifyingly real. For centuries, the Byzantine Empire held a naval secret so potent it could decide the fate of cities, a weapon known to history simply as Greek fire. Imagine the scene from the deck of an enemy ship approaching Constantinople. From the bow of a seemingly ordinary Byzantine dromon, a strange tube, often shaped like a bronze lion or dragon, would project not a solid missile, but a roaring, liquid stream of flame. This was no ordinary fire. Upon hitting the water, it did not sputter and die. It clung and spread, creating a blazing carpet on the very surface of the sea that was nearly impossible to extinguish. Water seemed only to feed its fury. Sand and vinegar were said to be the only reliable ways to smother it, but on the open deck of a wooden warship, such materials were rarely at hand in sufficient quantity. The psychological impact was as devastating as the physical. Sailors faced an elemental nightmare, a fire that chased them across the waves, igniting their ships, their sails, and the sea itself around them. The weapon was the ultimate defensive tool for the Byzantines. used to brilliant effect in sieges like the defense of Constantinople in the 7th century, where it incinerated entire Arab fleets and saved the empire from collapse. Its exact recipe, however, was a state secret guarded with a level of security that would impress any modern government. The knowledge was compartmentalized, reportedly known only to a single family, the imperial chemists and the emperor himself. Manuscripts hint at ingredients that could include crude oil or naphtha from natural surface wells around the Black Sea, mixed with resins, sulfur, or quicklime. Some formulations may have included saltpeter, a precursor to gunpowder, though this is debated. The true genius and the enduring mystery likely lay not just in the flammable liquid itself, but in its delivery system. How was this volatile mixture pressurized and projected as a steady, continuous stream? The most plausible theory involves a complex pump and heating apparatus. A large bronze tank of the mixture would be heated to increase its pressure. A hand-operated pump, possibly with a leather bellows, would then force the liquid through a bronze tube mounted on the ship's bow. A crewman at the nozzle would hold a torch to ignite the stream as it emerged, creating the legendary jet of fire. The engineering challenges here are immense. Preventing the apparatus from exploding prematurely, maintaining consistent pressure, and protecting the crew from backflash or their own weapon required a level of metallurgical and mechanical skill that was far ahead of its time. This is why, despite centuries of speculation and experimentation, no one has ever conclusively replicated authentic Greek fire. We can create flammable liquids that burn on water, but we cannot be certain we have matched the precise combination of adhesion, intensity, and projectability that made the Byzantine weapon so uniquely fearsome. The secret died with the empire that cherished it. The loss of this formula is a poignant reminder that technological advancement is not always a steady, accumulating line. Sometimes it is a flickering torch passed carefully from one generation to the next that can simply be blown out by the winds of time, leaving behind only the echo of its roar and the ghost of its flame on the dark water. Beneath the quiet fields of Zhejiang province in China lies a hidden world of staggering scale. Discovered by accident in 1992 by a local farmer pumping water, the Longyou Caves are not a natural formation. They are a colossal, man-made subterranean complex, a series of at least 24 enormous caverns carved by hand from solid sandstone and siltstone. The numbers alone defy comprehension. Each cave is immense, with some spanning over 10,000 square meters, with ceilings supported by massive, evenly spaced pillars of untouched stone. The total volume of rock excavated is estimated at nearly 1 million cubic meters. To visualize that, picture removing enough stone to build 30 of the Great Pyramids of Giza, and then secretly burying the entire project underground. This was not a haphazard digging operation. The walls, ceilings, and pillars are covered in a uniform, decorative pattern of parallel chisel marks, each line etched at a consistent 60-degree angle, running in unbroken bands across vast surfaces. This precise, rhythmic patterning is not merely artistic, it is a signature of method. It tells us that every inch of this million cubic meter space was finished with the same deliberate, systematic technique, suggesting a massive, organized workforce following a single, rigorous standard over what must have been generations. The logistical questions are overwhelming. What tools could have been used to achieve this? The sandstone is hard, and the consistent angle and depth of the chisel marks rule out simple pounding with stone hammers. Some form of hardened metal tools would have been necessary, yet no tools, no workshops, and no debris from this unimaginable excavation have ever been found. Where did they put the 1 million cubic meters of rubble? It simply vanished from the archaeological record. Then comes the most haunting question of all: purpose. These are not tombs, no remains or burial goods have been found. They are not living quarters with no evidence of hearths or daily life. they show no signs of being mines, as the stone itself has no special value. The caves are purely and mysteriously architectural spaces, grand halls built for an unknown function, then completely sealed and forgotten for possibly 2 millennia. The sheer, inexplicable investment of labor points to a motive of profound cultural or spiritual importance, a reason so compelling it justified moving a mountain only to hide it again. Modern engineers equipped with jackhammers and dump trucks could replicate the excavation, but they cannot replicate the why. To stand in the damp silence of these caverns is to feel the weight of a vanished intention. The uniform chisel marks on the walls become a kind of language, a message from the workers that we can see but cannot read, telling of a purpose grand enough to carve a secret cathedral into the belly of the earth, and then take its reason with them when they left. The silent, perfect halls of Longyou ask a question about purpose that may never be answered. In the high plains of Bolivia, another site offers a different kind of silence, one not of hidden space, but of shattered perfection. The ruins of Pumapunku, part of the greater Tiwanaku complex, look at first glance like a scene of catastrophic destruction. Giant stone slabs and intricately shaped blocks lie scattered across the landscape as if a giant's toy box had been overturned. But to look closer at any one of these pieces is to experience a profound sense of dislocation. These are not rough-hewn stones. They are components of a precision engineering project, frozen in a state of abrupt and violent disassembly. The most famous artifacts are the so-called H-blocks, massive modules carved from andesite, an exceptionally hard volcanic stone. Each block is identical in its dimensions and features a series of complex, recessed notches and protruding tabs. These are not decorations, they are interlocking joints, designed to fit together with neighboring blocks with absolute precision, like pieces of a giant, 3-dimensional stone puzzle. The surfaces of these blocks are not merely smooth, they are perfectly flat and polished to a degree that rivals modern machine work. The edges are razor-sharp, the corners are perfect 90-degree angles, and the geometric patterns are replicated across multiple blocks with no measurable deviation. This level of exactitude presents a clear and troubling question for conventional archaeology. How did the Tiwanaku culture, which flourished from around 500 to 1000 of the Common Era, achieve this? The standard toolkit of the period included stone hammers and bronze chisels, tools utterly incapable of producing the microscopic precision seen on these andesite blocks. You cannot create a flawlessly flat surface over a square meter using a handheld hammerstone. You cannot carve intricate, interlocking joints with tolerances of less than a millimeter using a soft bronze chisel on one of the hardest stones available. The replication challenge here is not about scale or logistics, but about the fundamental tools of fabrication. Modern engineers could, of course, recreate these blocks using computer-controlled diamond-tipped saws and milling machines. But to do it with the technology historically assigned to the Tiwanaku is considered effectively impossible by many stonemasons and engineers who have studied the site. The stone itself shows no signs of the pounding or pecking marks associated with hand tools, only clean, precise cuts. This has led to persistent speculation about lost methods. Could they have possessed a technique for softening the stone temporarily, perhaps with a plant-based chemical agent, allowing it to be shaped before re-hardening? Or does the evidence point to a more advanced and now completely lost form of machining technology? The purpose of these blocks deepens the mystery. They were clearly part of a larger, modular structure, perhaps a temple platform or a monumental gateway. The interlocking design suggests a building meant to withstand seismic activity, a smart adaptation in a geologically active region. But the effort invested in the precision far exceeds mere structural necessity. It speaks of a cultural obsession with geometric perfection, a desire to create order so exact it feels mathematical, imposed upon a chaotic natural material. To walk among the ruins of Pumapunku is to walk through a field of perfect questions. Each scattered H-block is a fragment of a blueprint we can no longer read, a piece of a syntax written in stone that we can recognize as brilliant but cannot reassemble into a coherent sentence. They stand as a direct tactile challenge to our timeline of technological progress, silent witnesses to a school of craftsmanship that appears, performs miracles in andesite, and then vanishes, leaving behind only its shattered components as proof that it was ever here at all. A different kind of stone refuses to give up its secrets. In a vault at Yale University rests a small, unassuming book, just over 200 pages bound in vellum. To the untrained eye, it looks like a medieval herbal or an alchemist's notebook, filled with strange, delicate illustrations of plants that do not exist, astrological diagrams, and scenes of tiny, nude figures bathing in interconnected pools of green liquid. But it is the text that has driven scholars, cryptographers, and intelligence agencies to distraction for over a century. Every page is covered in an elegant, flowing script written in an alphabet that is completely unknown. This is the Voynich Manuscript, and it is arguably the most stubbornly unreadable book in the world. Its characters are beautifully formed, with a consistent structure that suggests a real language, not random gibberish. The words follow patterns, with certain characters appearing only at the beginnings or ends of words, much like any natural language. Yet, despite over 100 years of analysis by the world's best codebreakers, including teams from the First and Second World Wars who cracked far more complex military ciphers, not a single word, not one sentence, has been definitively decoded. It is a locked door for which no key has ever been found. The manuscript represents a unique engineering feat, not of physical construction, but of information design. Someone or some group went to immense effort to create a complete, self-contained system of communication, a visual and linguistic architecture meant to convey specific knowledge, and then successfully hid its meaning from everyone who has come after. The illustrations offer tantalizing, frustrating clues. The botanical section shows plants with detailed roots, leaves, and flowers, but they are fantastical hybrids, composites of real species that could never grow. The biological section depicts those mysterious bathing figures, arranged in what look like plumbing diagrams, suggesting a lost understanding of human anatomy or perhaps a spiritual process. The astronomical section has circular diagrams of stars and zodiac symbols, but their arrangements match no known medieval cosmology. Every potential path to understanding leads to a dead end. Statistical analysis proves the text has the complex structure of language, ruling out a simple hoax. Yet every attempted decipherment, whether treating it as a coded version of Latin, Hebrew, or a constructed language, has collapsed under scrutiny. The replication challenge here is intellectual and profound. Could you, using only the knowledge and tools available in 15th century Europe, create a 200-page book that would completely resist the computational power and linguistic science of the 21st century? To do so would require a cryptographic genius far ahead of its time, or a completely novel way of organizing information that we have not yet thought to look for. The Voynich Manuscript is a monument to the power of a secret. It stands as a silent testament to the fact that the most advanced engineering is not always about moving mass or defying gravity. Sometimes it is about constructing an idea so carefully, weaving meaning into form so intricately, that it becomes a perfect enigma, a castle built not of stone but of symbols whose walls have never been breached. Off the coast of Japan's westernmost island, the ocean floor holds a structure that looks like a sunken city. Known as the Yonaguni Monument, this massive formation lies about 80 feet beneath the waves, a sprawling complex of flat terraces, sharp 90-degree angles, and what appear to be staircases and pillars carved from solid sandstone. Discovered by a diver in 1986, it immediately sparked a fierce debate that continues to this day. Is this a stunning example of natural geology, shaped by millennia of tidal currents and seismic fracturing, or is it the eroded remnant of a civilization that built here when this land was above water, thousands of years ago? The visual evidence is compelling. There are broad, level platforms that look like plazas. There are two tall, pillar-like stones that stand close together, resembling a ceremonial gate. Most strikingly, there is a structure nicknamed the Turtle, a flat-topped rock with a clear, geometric outline that looks deliberately shaped. Proponents of the human origin theory point to these features, arguing that nature rarely produces such clean, repetitive right angles and symmetrical steps in a single locale. They suggest the monument could be part of a ceremonial complex, perhaps related to other ancient cultures in the region, that was submerged at the end of the last ice age as sea levels rose. If that is true, it would push human monumental engineering back by over 10,000 years, a timeline that radically alters our understanding of prehistory. The opposing scientific view is equally fascinating. Geologists note that the sandstone in this area has strong horizontal bedding planes, which can fracture along straight lines under tectonic stress. They demonstrate how the powerful currents in the area can erode rock along these natural fractures, creating flat surfaces and blocky shapes that can mimic architecture. The entire formation, they argue, is a magnificent example of a natural, layered sandstone mesa that has been sculpted by the sea. The debate itself is the real engineering puzzle. If humans did build it, the challenge they faced was monumental in a literal sense. They would have been working on a coastline, quarrying and shaping this relatively soft sandstone with stone tools. But the greater, almost inconceivable challenge comes from the timeline. To have been built above water, the structure would have to date to a period before the sea level rose to engulf it, a process that occurred roughly 10,000 years ago. This places its construction, if it is artificial, in a prehistoric era for which we have almost no record of complex stone architecture anywhere on Earth. The replication challenge, therefore, is twofold. First, could ancient humans with primitive tools have created such large-scale, geometric forms in sandstone? The answer is possibly yes, given enough time and labor, but the second challenge is far more profound. Could they have done it at a time when, according to mainstream archaeology, human societies were just beginning to settle into agricultural life? This is the true weight of the Yonaguni mystery. It forces us to look at a landscape, or rather a seascape, and decide what we are seeing. Are we projecting our own desire for lost cities onto the beautiful, random artistry of nature? Or are we witnessing the stubborn, drowned evidence of a chapter of human achievement so old its very memory has been washed away by the rising tides? The monument sits in that haunting space between a rock and a hard place, between geology and history, inviting us to question not just what is possible for nature to create, but what might be possible for a forgotten culture to have dreamed and built on the edge of a world that would one day vanish beneath the waves. The Yonaguni debate is a question of scale and time, but some stones leave no doubt about the hands that moved them. In the Bekaa Valley of Lebanon, the ruins of the Roman temple complex at Baalbek are monumental by any standard. Yet, beneath the familiar columns and courtyards lies a far older, more bewildering feat of engineering. The temple's foundation platform is built upon a course of stones so colossal they seem to belong to the realm of myth. These are the Baalbek Megaliths, and three of them, known as the Trilithon, are each approximately 64 feet long, 14 feet high, 11 feet wide, and weigh an estimated 800 tons. To put that in perspective, each one of these blocks is heavier than a fully loaded Boeing 747 airplane. They were quarried from a site nearly a mile away, dragged to the Temple Mount, and then lifted over 20 feet in the air to be fitted together with a precision that leaves hairline joints. The Romans, master builders that they were, simply used this pre-existing Cyclopean platform as the base for their own temple, as if even they recognized they were building upon the work of giants. But the true showstopper lies still in the quarry. A short distance from the temple, resting in a trench, is the stone of the pregnant woman. This single block of limestone was cut and prepared but never moved. It is even larger than the trilithon stones, measuring an astounding 69 feet long, 16 feet wide, and 14 feet high, with a weight estimated at 1,000 tons. It is the largest known worked stone from antiquity. The process of quarrying alone is a puzzle. How do you undercut and separate a 1,000-ton block from the living bedrock without modern diamond wire saws or explosives? The likely method involved teams of workers carving deep channels around the intended block using simple iron chisels and hammers, a process of relentless pounding that would have taken months, if not years, for a single stone. Then they would have driven wooden wedges into slots along the base, soaking them with water so the expanding wood would gradually, with immense pressure, crack the stone free from the quarry floor. This is a test of patience and coordination on an almost unimaginable scale, but quarrying is only the first act. The real logistical nightmare is transportation. How do you move a 1,000-ton block a mile over uneven ground? The conventional theory for the 800-ton trilithon stones involves a system of ropes, wooden sledges, and legions of laborers. The road would have been paved with logs as rollers, and teams of men or oxen, potentially numbering in the thousands, would have pulled with a coordinated rhythm, inch by agonizing inch. Engineers calculate that moving such a mass would require overcoming immense friction, a task that pushes the limits of what human and animal power can achieve, even with the clever use of grease or mud as a lubricant. The final act, lifting these behemoths 20 feet into the air to form the temple's foundation course, is perhaps the most debated. The most plausible method is an enormous earthen ramp. Workers would have built a sloping ramp of compacted earth and rubble leading up to the construction site. The stone, still on its sledge, would be dragged up this ramp. Once at the correct height, it could be painstakingly levered off the sledge and into its final position, after which the ramp would be dismantled. This method, while straightforward in theory, is staggering in its execution. The ramp for an 800-ton stone would have been a massive public works project in itself, requiring the movement of even more earth and stone than the block it was designed to lift. The replication challenge for modern engineers is not about whether we could move such stones. We have cranes and transporters that could manage it. The challenge is doing it the ancient way, with only human and animal power, ropes, wood, and levers. Recent experiments with much smaller stones in the 100-ton range have shown how difficult, dangerous, and slow such an operation is, requiring exquisite teamwork and constant danger of catastrophic failure. The Baalbek Megaliths, therefore, stand as a testament to a society with an almost frightening degree of social organization and political will. They represent a decision made by someone to invest the entire energy of a civilization into moving mountains, not for immediate practical need, but to create a foundation of such overwhelming, undeniable power that it would echo through millennia. They are a statement carved in limestone, a declaration that here human ambition reached a scale that still makes our machinery seem humble and our understanding of the past seem incomplete. While the Baalbek stones represent a triumph of sheer mass, a different kind of power was being forged in the hands of a warrior. Across the battlefields of early medieval Europe, a name whispered of both terror and supreme craftsmanship, Ulfberht. These were Viking swords, but not the crude, often brittle iron blades of popular imagination. And Ulfberht was something else entirely, a weapon of such consistent, superior quality that it was the equivalent of a modern precision rifle among muskets. The name itself, inlaid into the blade with iron and nickel lettering, was not a maker's mark in the traditional sense, but a brand, a guarantee of performance that spanned over 2 centuries and hundreds of surviving examples. The secret was not in the design, which was a classic, double-edged Viking style, but in the material. Metallurgical analysis has revealed that genuine Ulfberht blades were made of a high-carbon steel of astonishing purity. This was not the common, slag-ridden, bloomery iron of the era, which was full of impurities that made it weak and prone to shattering under stress. Ulfberht steel was nearly as pure as modern crucible steel, with a carbon content around 3 times higher than its contemporaries. This high carbon content gave the blade remarkable properties. It could be honed to a sharper, more resilient edge that would hold its keenness in the chaos of a shield wall. More importantly, it possessed a perfect balance of hardness and flexibility. A lesser sword might bend permanently or snap in a brutal parry, but an Ulfberht could flex and spring back to true, a life-saving characteristic for its wielder. The engineering mystery lies in how this steel was made. To achieve such purity and consistent carbon content requires a furnace that can reach temperatures far beyond what typical European forges of the 9th to 11th centuries could manage. The common bloomery furnace, which uses charcoal to melt iron ore directly, produces a spongy mass of iron and slag. To make Ulfberht steel, the metal had to be liquefied completely. This allows the impurities, which are lighter, to separate and rise to the surface as glassy slag, leaving behind a homogeneous pool of liquid steel. This process, known as crucible steelmaking, requires sustained temperatures of around 3,000 degrees Fahrenheit. The technology for this was not common in Europe until the Industrial Revolution, nearly 800 years later. So how did the makers of Ulfberht achieve it? The prevailing theory points east, along the vast river trade routes connecting the Viking world to the Islamic Caliphate. Central Asian steelmakers, particularly in modern-day Uzbekistan and Turkmenistan, had mastered crucible steel production, creating famous Damascus steel ingots known as woots. It is highly probable that Ulfberht blades began as these imported ingots of ultra-pure steel, traded north along the Volga River, and were then expertly forged and inscribed by Frankish or Rhineland smiths who understood their incredible value. This makes the Ulfberht not just a weapon but a fossil of global trade, a product of metallurgical knowledge that flowed thousands of miles from its origin to the hands of a Norse raider. The replication challenge is profound. Modern blacksmiths can, with advanced equipment, recreate the steel, but to do it with period technology in early medieval Europe, as the inscription seems to imply, remains nearly impossible. The Ulfberht sword, therefore, stands as a gleaming paradox. It is a symbol of the Viking Age, yet its essence was born from a technological exchange with a culture far to the southeast. It represents a fleeting window where a supply of perfect material met masterful craftsmanship, creating a legendary tool that was both a marvel of its time and a ghost from the technological future. Its bright edge reflecting not just the fire of a northern forge, but the distant, brilliant heat of a crucible furnace on the Silk Road. The gleam of a perfectly forged sword speaks of a culture's technical prowess in conflict, but a society's true engineering genius is often revealed in how it manages the most fundamental elements of life. While warriors prized the Ulfberht's edge, an entire civilization on the island of Crete was perfecting a different kind of flow, one of pure, clean water and efficient waste. The Palace of Knossos, the heart of the Minoan civilization that thrived over 3,500 years ago, was not just a political center. It was a marvel of hydraulic engineering, a living machine built around water. Its advanced plumbing and sanitation systems were so sophisticated they would not be matched in Europe for another 3 millennia. At a time when many contemporary cultures considered running water a luxury of nature, the Minoans engineered it as a controlled, integrated utility. The entire complex was laced with a network of meticulously crafted terracotta pipes. These were not simple clay tubes. Each pipe section was carefully tapered, designed to fit snugly into the next, with a narrower end pointing in the direction of the flow. This ingenious design created a self-sealing joint that prevented leaks and increased water pressure as it moved through the system, a principle still used in modern plumbing. These pipes channeled fresh spring water from the surrounding hills into the palace, supplying fountains, bathing areas, and the royal quarters. But the true stroke of brilliance lay in what happened after the water was used. The Minoans did not let waste accumulate. In private quarters, archaeologists have discovered the earliest known flushing toilets. These were not mere pits. They were sophisticated stone seats with a wooden lid connected to a hidden drainage system. A conduit built into the wall would carry rainwater or manually poured water to flush waste away through the terracotta pipes and into a main sewer that ran beneath the palace floors. This was a closed, sanitary system that separated clean living spaces from the byproducts of daily life, a concept of public health that was revolutionary for its era. The foresight extended beyond the interior. The palace designers understood the threat of seasonal rains. They constructed an extensive network of stone-lined storm drains and culverts that ran alongside walkways and under courtyards. These channels efficiently captured runoff during heavy downpours, preventing flooding and erosion, and directing the water safely away from the living and storage areas. The entire system was a coordinated, gravity-fed masterpiece. Water entered at the highest point of the complex, flowed through the pipes to where it was needed, carried away waste, and finally merged with storm runoff to be discharged, all without pumps or any power source other than the natural slope of the land. To walk through the ruins of Knossos today is to see the ghost of this invisible network. The sunken channels, the strategically placed shafts for cleaning and access, the carefully graded floors all point to a culture that viewed water management not as a chore, but as a foundational pillar of civilized life. Their engineering was not about monumental display, but about creating a healthy, sustainable, and pleasant environment. It was a quiet, practical genius flowing beneath their feet, a hidden infrastructure that made their advanced culture possible, proving that the highest form of ancient technology was sometimes the one you never had to see, only the one you could always rely on. Yet the flowing water of Knossos speaks of a settled, urban mind. To find the very origin of that impulse, we must travel to a barren hill in southeastern Turkey, where the stones tell a story that upends the fundamental timeline of human civilization. Göbekli Tepe is not a city nor a palace. It is a series of circular enclosures built not by farmers, but by hunter-gatherers over 11,000 years ago, a staggering 7 millennia before the Great Pyramid of Giza. At its heart are massive limestone T-shaped pillars, the heaviest weighing over 16 tons. These are not crude monoliths. They are elegantly shaped with smooth, finished sides and carved reliefs of animals so vivid they seem to pulse on the stone. Scorpions, foxes, boars, and birds, a menagerie frozen in a predatory dance. The mystery here is not just one of engineering, but of motive. According to traditional archaeology, monumental architecture is a product of settled agricultural society. Farming creates surplus food which supports specialized labor, leading to social hierarchy and the large-scale projects that display power and belief. Göbekli Tepe shatters that sequence. Here, at the dawn of the Neolithic, people who still lived by hunting and gathering came together to undertake a project of breathtaking ambition. They quarried these colossal pillars from nearby limestone bedrock using stone tools. The process likely involved carving channels around a pillar shape and then using wooden wedges and water to fracture it free, a task requiring immense coordination and knowledge of the material. Then they shaped them. The T form is precise, with the crossbar of the T representing stylized human arms and the pillar itself an abstract human figure. This suggests a symbolic language, a shared mythology powerful enough to motivate the work. After shaping, They transported these multi-ton pillars hundreds of yards and erected them into circle formations, slotting them into sockets carved into a shared bench of bedrock. The logistics are mind-bending. Without beasts of burden, without wheels, the movement and erection of each pillar would have required the coordinated muscle of hundreds of people, likely drawn from different nomadic bands across the region. This implies a social organization far more complex than we ever attributed to hunter-gatherers. They were not just surviving, they were convening for a purpose that transcended immediate need. The site shows no evidence of permanent settlement, no houses or granaries. It appears to have been a purely ritual space, a sacred hill where scattered groups periodically gathered to build, to carve, and to enact ceremonies we can only guess at. The animals on the pillars are not docile farm creatures, but wild, powerful, and dangerous. They may represent guardian spirits, totemic ancestors, or a complex spiritual relationship with the hunted world. After each enclosure was used for perhaps generations, it was deliberately and carefully buried, filled with thousands of tons of soil and stone, preserving it for modern discovery. Why bury your greatest achievement? Was it an act of reverence or a way to seal a covenant? The replication challenge at Göbekli Tepe is multifaceted. It asks us to replicate not just the physical act of moving multi-ton stones with primitive technology, which is difficult enough, but to replicate the social and psychological conditions that made it possible. How do you convince nomadic hunter-gatherers whose lives are focused on daily sustenance to invest years of backbreaking labor for a symbolic structure? The answer must lie in a shared belief so potent, so unifying, that it became the engine for engineering itself. Göbekli Tepe suggests that the drive to build monumental architecture, to express collective identity and belief in permanent form, may not be a consequence of agriculture and civilization. It may be the very spark that ignited them. The need to gather, to work together on this scale, could have been the catalyst for developing agriculture to support such gatherings. The pillars, then, are not a product of settled life, but its profound and mysterious cause. They stand as the earliest known architects of our social world, silent T-shaped questions carved into a hill, asking us to reconsider which came first, the farm or the faith that moved mountains. The pillars of Göbekli Tepe were monuments to a collective belief, a shared idea made solid. But what if the most important idea to capture was not a spiritual one, but a physical warning, a tremor in the earth itself? In the year 132 of the Common Era, during China's Han Dynasty, a court scholar and inventor named Zhang Heng presented the emperor with a device that seemed to possess a supernatural sense. It was a large, ornate bronze vessel, nearly 6 feet in diameter, shaped like a ceremonial wine jar. 8 dragons adorned its surface, each with a bronze ball held delicately in its jaws. Crouched below each dragon, with mouths open in anticipation, sat 8 corresponding bronze toads. This was not a decorative sculpture. It was the world's first seismoscope, an instrument designed to detect the direction of distant earthquakes that no human at the court could yet feel. The principle, as described in historical records, was one of elegant mechanical intuition. Inside the sealed vessel, Zhang Heng placed a carefully balanced central pendulum. Around this pendulum, he arranged a series of cleverly crafted levers, connected to the jaws of the 8 dragons which pointed toward the 8 cardinal directions. When a seismic wave from a far-off quake reached the capital, it would cause the ground to tremble ever so slightly. This subtle motion would upset the delicate balance of the internal pendulum. The swinging pendulum would then strike one of the directional levers, triggering a mechanism that caused the corresponding dragon on the outside to open its jaws. The bronze ball would drop, clattering into the waiting mouth of the toad below with a loud, ringing report. The direction of the earthquake's epicenter was thus dramatically announced by which toad received the ball. Historical accounts claim the device worked with uncanny accuracy, once detecting a quake hundreds of miles away that was confirmed days later by messengers from the afflicted region. The true engineering marvel lies in the proposed internal mechanism, to be sensitive enough to react to faint, distant tremors, yet specific enough to actuate only one directional lever amidst the general shaking, suggests a level of mechanical sophistication that rivals the finest clockwork. The replication challenge for modern engineers and historians is profound. While the outward design is clear, the exact arrangement of the internal levers and the pendulum's precise pivot mechanism are lost to time. Several teams have built working replicas based on plausible interpretations, using inverted pendulums or suspended masses. Some have succeeded in demonstrating directional sensitivity. Yet, no modern replica has ever matched the legendary sensitivity and reliability described in the ancient texts under rigorous scientific testing. The central difficulty is one of signal versus noise. How did Zhang Heng's mechanism filter out the constant minor vibrations of a busy palace, footsteps, carts, distant drums, to react only to the unique signature of a long-period seismic wave? Some theories suggest the internal mechanism may have employed a form of inertia, where only a sustained, rhythmic motion in one direction would accumulate enough force to trip the lever, a concept far ahead of its time. The device stands as a breathtaking leap in scientific thought. It represents a moment when humanity moved from merely fearing natural disasters to attempting to instrument them, to translate the invisible language of the earth into a visible, actionable signal. Zhang Heng sought to give the empire an early warning system, turning mysterious subterranean fury into a simple, ringing sound in a courtyard. That ambition to make the imperceptible perceptible is the very heart of engineering. His seismoscope may guard its final secret within its bronze shell, but its legacy is clear. It marks the dawn of a new relationship with our planet, one built not on superstition, but on observation, mechanics, and the relentless desire to listen to the world's deep and hidden movements. The desire to listen to the Earth's hidden movements is a profound form of knowledge, but so too is the ability to move the Earth itself, alone, in secret. In the humid Florida landscape of the early 20th century, a single man performed a feat that seems pulled from the age of megaliths. Edward Leedskalnin, a frail Latvian immigrant standing just 5 feet tall and weighing barely 100 pounds, spent 28 years single-handedly building what he called Rock Gate Park, later known as the Coral Castle. Using no modern machinery, no assistance, and working almost exclusively at night to avoid prying eyes, he quarried, shaped, transported, and erected over 1,100 tons of oolitic limestone, a material as hard as coral. The blocks are massive, with the largest weighing an estimated 30 tons, equivalent to a full-sized school bus. He carved them into intricate forms, a 9-ton gate that swung open with the touch of a finger, a 22-ton obelisk, perfectly proportioned tables and chairs, and a functioning sundial accurate to within 2 minutes. The how of it remains one of the great modern puzzles of manual engineering. Leedskalnin was famously secretive, shrouding his worksite with tall walls of stacked coral and offering only cryptic hints about his methods. He claimed to have rediscovered the building secrets of the ancient pyramid builders, stating he understood the laws of weight and leverage. Visitors would hear him singing softly as he worked, and sometimes the sound of clinking chains, but they never saw him actually moving the stones. He left behind only a few simple tools, homemade tripods of timber, metal chains, and a collection of old car parts. The prevailing theory is that he was a master of leverage and counterweight, using block and tackle systems and a clever understanding of center of mass to pivot and lift the immense blocks. He may have used the tripods as makeshift cranes, placing the stones on metal rollers or spheres to reduce friction, then inching them along with levers. Yet, when engineers and physicists examine the precision of his work, especially the perfectly balanced 9-ton gate that rotated on a metal shaft with no apparent ball bearings, they admit the sheer efficiency of his solo operation defies easy explanation. How did one man, without formal education or modern power tools, achieve such precise results? Leedskalnin's own writings delve into magnetism and what he called perpetual motion holders, leading to speculation that he somehow used electromagnetic principles or acoustic levitation, though no evidence supports this. The true replication challenge of the Coral Castle is not about moving 30-ton stones. We have machines for that. The challenge is moving them as he did, with minimal equipment, maximum secrecy, and an almost supernatural economy of effort. It forces us to consider that the lost methods of antiquity might not have required thousands of slaves, but perhaps a deep, intuitive understanding of physics possessed by a few master builders. Edward Leedskalnin stands as a lonely, modern echo of those ancient engineers. He did not just build a castle of coral, he built a monument to the power of a single, determined mind, proving that the greatest feats are sometimes not about the scale of the workforce, but the depth of the secret one man can hold and take with him when he is gone. The silent, solitary work of one man stands in stark contrast to the greatest communal project of prehistoric Europe. On the broad, windswept Salisbury Plain, the familiar Sarsen stones of Stonehenge form its iconic outer ring and trilithons. But the true, deep mystery of the site is held by the smaller, inner circle of bluestones. These are not local rocks. Their unique geology traces them over 150 miles away to the Preseli Hills in southwest Wales. This fact presents one of the most enduring logistical puzzles in archaeology. How, around 5,000 years ago, did Neolithic communities move 80 or more of these multi-ton stones across a landscape of mountains, rivers, and dense forest? The bluestones, each weighing up to 4 tons, are a type of spotted dolerite, a hard, volcanic rock prized for its distinctive appearance. The journey from quarry to final resting place represents a feat of intention so powerful it challenges our understanding of prehistoric capability and motivation. The debate centers on a fundamental question: was this a human endeavor, or did nature do the heavy lifting? One scientific camp proposes a glacial transport theory. During the last ice age, massive glaciers could have acted as natural conveyor belts, plucking bluestones from the Welsh hills and depositing them much closer to Salisbury Plain as the ice retreated. If true, Neolithic builders would have simply collected these conveniently placed, exotic stones from a nearby glacial deposit. This theory offers a pragmatic solution, reducing the required human effort from the impossible to the merely monumental. However, recent geological studies have complicated this tidy explanation. Detailed analysis of the specific bluestones at Stonehenge has matched them not just to the general Preseli region, but to very specific outcrops like Carn Godog and Craig Rose y Felin. The evidence suggests these stones were quarried deliberately from those precise locations, not scavenged from a random glacial scatter. Tool marks and evidence of stone working at these Welsh quarries strongly indicate human agency from the very beginning. This points toward a staggering, deliberate undertaking. If humans moved them, the scale of the operation becomes almost incomprehensible. The most plausible human transport theory involves a combination of land and water routes. After being quarried and roughly shaped, each stone would have been hauled on a sledge made of timber, dragged by teams of people using ropes. They would have navigated the rugged Welsh terrain, then faced the daunting challenge of the water crossing, likely the Bristol Channel or the Severn Estuary. Here, the stones would have been transferred onto rafts or floated alongside canoes, a perilous operation in tidal waters. After landing on the southern English coast, the overland haul would begin again, covering the final dozens of miles to the plain. The sheer labor involved is staggering. Conservative estimates suggest moving a single 4-ton bluestone. This distance would require hundreds of people working in coordinated shifts, not for days but for months. It would demand advanced knowledge of seasonal weather, river currents, and tide patterns. It would require a social structure capable of organizing and sustaining such a workforce, feeding them, and maintaining a shared purpose across generations. This is where the mystery transcends engineering and enters the realm of belief. Why go to such extraordinary lengths for these particular stones? The answer likely lies in their origin. The Preseli Hills were not just a source of nice rock, they were a sacred landscape imbued with spiritual power and ancestral significance. By transporting stones from this holy place, the builders were not just moving mass, they were physically bringing the essence of that distant, powerful land to their own ceremonial center. The bluestones were likely believed to hold intrinsic properties, healing or magical, that made the unbearable effort not just worthwhile but necessary. The act of moving them may have been a ritual in itself, a profound pilgrimage that transformed the landscape into a pathway of faith. Modern attempts to replicate the journey have proven just how difficult it truly is. In a famous experiment in the 1950s, a team using a wooden sledge, ropes, and volunteers managed to move a concrete replica of a bluestone, but the process was agonizingly slow and fraught with danger, highlighting the immense skill and experience the original builders must have possessed. The Bluestones of Stonehenge, therefore, are more than architectural components. They are the physical evidence of a journey, a testament to a culture that measured distance not in miles but in collective will. They force us to choose between two narratives, one of pragmatic opportunism, using stones left by a glacier, and one of breathtaking spiritual ambition, moving mountains to make a sacred connection across the very bones of the land. Whichever story is true, the silent, spotted stones at the heart of the circle remind us that for our ancestors, some ideas were so powerful they were worth carrying, step by agonizing step, across the width of a world they were only just beginning to map. But the stones of Stonehenge were moved for a sacred purpose, a connection between landscapes. In the highlands of central Mexico, an entire city was built as a mirror of the cosmos. Teotihuacan, the city of the gods, is a masterpiece of urban planning on a scale that feels both human and divine. Its central axis, the Avenue of the Dead, is not a simple road. It is a carefully surveyed baseline, a celestial measuring tape laid across the valley floor for over 2.5 miles, running precisely 15.5 degrees east of true north. This specific, intentional orientation was not arbitrary. It aligns with the setting point of the Pleiades star cluster on a key ceremonial date, and its entire grid is geometrically integrated with the surrounding mountain peaks, creating a sacred landscape where architecture and nature spoke the same silent language. The harmony is breathtaking. The massive Pyramid of the Sun, one of the largest structures of the ancient world, sits just east of the avenue. Its base perimeter is nearly identical to that of the Great Pyramid of Giza, yet its design serves a different master. The pyramid's west face is perfectly aligned to frame the setting sun on the days of its zenith passage, when the sun reaches its highest point directly overhead, casting no shadow. This alignment required not just astronomical observation, but the ability to translate that observation into a fixed, immovable stone reality across a vast distance. Even more precise is the smaller, exquisitely proportioned Pyramid of the Moon at the avenue's northern terminus. It does not sit parallel to the avenue, but is carefully angled so that its facade perfectly frames the majestic Cerro Gordo mountain behind it, making the man-made pyramid appear as a natural extension of the sacred mountain itself. This is urban planning as a form of poetry, a dialogue between earth and sky, stone and horizon. The engineering feat here is one of sustained vision and meticulous execution. To lay out a city of this magnitude, covering 8 square miles, with such consistent alignments required a level of surveying knowledge that seems almost modern. The builders used a standard unit of measurement, approximately 83 centimeters, which is found repeated in the dimensions of platforms, plazas, and buildings across the site. They understood how to create level foundations on uneven terrain and how to manage water drainage across the entire urban grid. The entire city feels like a single, coherent thought, built over centuries by a culture whose name we do not even know. The people of Teotihuacan left no deciphered written records, yet they left a three-dimensional text written in stone and alignment. The replication challenge is not about moving a single massive block, but about replicating the holistic vision. Could modern city planners, with all their satellite imagery and laser levels, design a metropolis of such symbolic depth and geometric harmony, where every street and structure participates in a grand celestial pattern? Teotihuacan stands as a testament to a different kind of intelligence, one that saw no separation between engineering, astronomy, and spirituality. The city is a machine for living in cosmic order, a permanent calendar made of avenues and pyramids, asking us if our own modern cities, for all their technological marvels, have lost the art of speaking to the stars. A city aligned to the cosmos speaks of a mind that saw patterns in everything. For the artisans of ancient Sri Lanka, that pattern was found not in the stars, but in the very first step you took into a sacred space. Carved from single slabs of granite or limestone, the moonstones at the entrances to Buddhist monasteries and palaces are not mere doormats. They are intricate, concentric maps of a spiritual journey, rendered in stone with a delicacy that seems to defy the hardness of their material. Each moonstone is a perfect semicircle, a series of carved bands that ripple outward from the center like waves from a dropped pebble. The outermost ring is almost always a line of flickering flames, a boundary of pure energy. Moving inward, you then pass through a procession of animals, each representing a state of being: the elephant for birth, the horse for aging, the lion for illness, and the bull for passing. This is the cycle of earthly life, of suffering and impermanence. Next comes a vine of lotus petals, symbolizing the rise toward purity. Finally, at the very center, you reach a single lotus flower, the ultimate symbol of enlightenment, of breaking through the surface of worldly existence into clarity and peace. The entire design is a profound philosophical statement, a visual sermon about the path from ignorance to wisdom, compressed into a space you physically cross over. The engineering marvel here is one of miniature perfection on a monumental scale. To carve these intricate, layered symbols into granite, one of the hardest stones, using only hand-held chisels and hammers, is an act of almost superhuman patience and control. The lines are crisp and deep, the curves of the lotus petals fluid and identical, the animals rendered with a lively, expressive detail that makes them seem ready to step off the stone. The craftsmen had to work with an unforgiving material. A single misplaced strike could shatter a delicate vine or ruin the symmetry of the entire piece. This required not just skill, but a deep, meditative focus, a union of artistic vision and physical discipline that turned the act of carving into a form of devotion itself. The challenge of modern replication lies in this very fusion of art, philosophy, and handcraft. A master stone carver today, using traditional tools, could perhaps recreate the physical form given enough time. But to replicate the moonstone is to replicate the entire cultural and spiritual context that gave it meaning. It was not decorative art, it was functional theology. Every person entering the temple, from the king to the commoner, would tread upon this map of existence, a constant, tactile reminder of the journey they were on. The stone itself, worn smooth by countless bare feet over centuries, became part of that journey, its physical erosion a testament to its use and purpose. To carve a moonstone was to encode a universal truth in a language of stone, a permanent lesson placed at the threshold between the profane world and the sacred interior. It asks us what we place at our own thresholds today, and what messages we consider important enough to carve not in fleeting pixels, but in the enduring heart of the earth. The journey from spiritual maps carved in stone leads to a landscape scarred by a more practical, yet equally mysterious, form of travel. On the Mediterranean islands of Malta and Gozo, the limestone bedrock is etched with a sprawling network of deep, parallel grooves known as the cart ruts. These are not random geological cracks. They are deliberate channels, often perfectly parallel and spaced a consistent distance apart, carved directly into the solid rock. They crisscross the islands, running up slopes, diving off cliffs into the sea, and intersecting in complex junctions that look eerily like ancient railway switchyards. The uniformity is startling. Each rut is typically between 8 and 15 centimeters deep, and the pairs are consistently spaced about 140 centimeters apart, center to center. This precise spacing is the first major clue, pointing not to natural erosion, but to a standardized vehicle of some kind. The prevailing theory is exactly what the name suggests, that these were created by carts, perhaps wooden sledges or wagons with solid wooden wheels, carrying heavy loads over the soft limestone. Over generations, the repeated passage of these carts along the same routes wore these deep grooves into the bedrock. The sheer depth of some ruts suggests centuries, if not millennia, of use, a testament to a relentless, established traffic pattern. But this simple explanation quickly unravels into deeper questions. What were they carrying that required such fixed, heavily trafficked routes? The islands have evidence of extensive prehistoric temple building and agriculture, so the carts could have been transporting stone blocks for construction, soil for farming, or water from springs. Yet the ruts often lead to puzzling places. Some run directly off sheer cliffs into the Mediterranean, suggesting either that the coastline has dramatically changed, or that the destinations, perhaps now submerged, were once ports or loading areas. Others climb steep inclines where dragging a heavy cart would seem almost impossible, and they sometimes intersect in ways that seem to lack logical order. This has led to alternative theories. Could the ruts be part of an ancient irrigation or water drainage system, though their parallel nature argues against this? Or were they slots for guiding something other than carts, perhaps for moving massive stone blocks on a fixed track, a kind of prehistoric railway? The most haunting possibility is that we are looking at the fossilized imprint of a lost industry, the physical evidence of a daily economic activity so vital it literally wore its signature into the face of the island, but whose ultimate purpose has faded from memory. The challenge of replication lies in the vehicle itself. What kind of cart creates such deep, clean, parallel grooves without itself being destroyed? Experiments with replica wooden sledges and carts have shown that, given enough time and weight, they can indeed wear grooves into soft limestone. However, achieving the uniformity and depth seen across the entire network, especially on slopes, would require a vehicle of remarkable durability and a cultural adherence to following the exact same path for generations. This speaks to a highly organized society with established transit corridors, a prehistoric highway code etched in stone. To stand at a junction of these ruts is to feel the ghost of that traffic, a silent hum of movement from a time when the island's lifeblood flowed along these stone channels. They are not monuments in the traditional sense, but a cumulative, accidental record of work. They ask us to consider what mundane, repeated actions of our own civilization might leave a permanent mark on the planet 10,000 years from now, and whether future archaeologists will understand the purpose of our own worn paths, or simply stare in wonder at the mysterious parallel scars we left behind. A network of stone paths stitches together the spine of a continent. While the Romans built their legendary roads across Europe, another empire high in the clouds of South America engineered a system of communication so advanced it defied the very mountains it crossed. The Inca road system, known as the Teotihuacan, was not a single road but a vast, interconnected web of highways spanning over 25,000 miles, from modern-day Colombia down through Ecuador, Peru, Bolivia, and into Chile and Argentina. This was the logistical backbone of the largest empire in the pre-Columbian Americas, and it was built without iron, without the wheel, and without draft animals. Its purpose was singular: to bind a sprawling, diverse empire of over 10 million people into a single, responsive organism under the rule of the Sapa Inca in the distant capital of Cusco. To achieve this, Inca engineers did not conquer the terrain, they collaborated with it. In the coastal deserts, they built raised causeways marked with posts to guide travelers through shifting sands. In the fertile valleys, they laid straight, wide roads flanked by walls. But the true genius of the system is revealed in the high Andes, where the empire's heart beat hardest. Here, the roads became feats of audacious engineering. On near vertical mountain slopes, they carved staircases and tunnels directly into the living rock. They built retaining walls to create level traverses across unstable scree, and constructed elaborate drainage systems to prevent erosion from torrential rains and melting snow. The roads were not paved in the Roman style, but surfaced with packed stone and gravel, designed for the sure-footed tread of llamas and human messengers. The most iconic and terrifying solutions were for crossing the empire's countless deep gorges and raging rivers. Instead of arches, the Inca mastered the suspension bridge, but not as we know it. They built braided bridges from natural fibers, primarily iku grass. The construction was a communal ritual. Villagers responsible for a bridge's upkeep would gather to weave massive cables, some as thick as a man's torso, from thousands of strands of grass. These cables were then carried to the canyon's edge, stretched across the abyss, and woven into a walkway, often with side rails of thinner fiber. The result was a bridge that swayed and bounced with every step, a dizzying passage over a roaring river hundreds of feet below. To modern eyes, it looks impossibly fragile, yet these bridges were remarkably strong and resilient, capable of supporting columns of soldiers and herds of llamas. They were not permanent structures in stone, but living ones in fiber, requiring complete renewal every year or two as the grass weathered, a duty that reinforced community bonds and ensured the empire's lifeline never snapped. This constant maintenance was the system's hidden strength. The empire was divided into administrative districts, each responsible for the roads and bridges within its territory. A system of way stations called tambos was spaced a day's journey apart, providing shelter, food, and supplies for imperial personnel. But the true power of the road was speed. Running along it was a corps of elite relay messengers, the chasquis. A message, often encoded in the knots of a quipu cord, could be carried from Quito to Cusco, a distance of over 1,200 miles, in about a week. A chasqui would sprint to the next tambo, shout his message to the waiting runner, and then rest while the information flew on, fresh legs carrying it at a running pace across some of the most punishing geography on Earth. This was an internet of flesh and stone, a real-time communication network that allowed the central government to administer justice, deploy armies, and redistribute resources across an empire of staggering ecological and cultural diversity. The replication challenge is profound. We could build a road through the Andes today with dynamite and diesel machinery. But to build the Teotihuacan the Inca way, to integrate it so seamlessly into a sacred landscape without causing catastrophic erosion, to organize the continuous, communal labor for its upkeep, and to sustain a messenger system that moved at the speed of a human runner across continental distances, that requires more than engineering. It requires a total social philosophy, a world view where the road was not just a path for travel, but a symbol of connection, an umbilical cord of stone and fiber that held a mountain empire together by sheer will, careful planning, and a deep understanding that to rule the land, you first had to respectfully, ingeniously join it. That same iron pillar holds a second, quieter marvel, one written not in its chemistry, but in its skin. Running vertically down its polished shaft is an ancient Sanskrit inscription, a proclamation carved over 1,600 years ago by a king named Chandra, likely Chandragupta II of the Gupta Empire. The words themselves record a king's devotion and military victories, a historical document of immense value. But the real engineering mystery is not what the inscription says, but how it looks. After 16 centuries of exposure to Delhi's punishing cycles of scorching heat, torrential monsoon rains, and modern urban pollution, the letters are not faint ghosts. They remain crisp, clear, and deeply carved as if they were cut just a few generations ago. This defies every expectation. Normal weathering on iron, even stable iron, should have blurred such fine detail long ago. Pitting, corrosion, and the buildup of oxides should have slowly eaten away at the edges of each character, filling them in and making them illegible. Yet, the inscription has resisted this fate. This suggests that the pillar's creators did more than just formulate a perfect alloy. They also perfected a method of preparing and protecting the surface that would receive their message for the ages. The technique is lost to us, but we can speculate. Perhaps after the inscription was carved, the surface was treated with a chemical agent, a heated oil or resin that sealed the fresh metal from immediate oxidation. Or maybe the process of polishing the pillar to its mirror-like finish, using fine abrasives over countless hours, created an ultra-dense, work-hardened surface layer on the metal that was far more resistant to the slow creep of corrosion than the underlying material. This would mean the scribe and the metallurgist worked in concert, the writer's chisel following a path prepared by the smith's art. The inscription, therefore, is a dual legacy. It is a historical record, yes, but it is also a permanent demonstration of a forgotten finishing technology. It proves that the ancient artisans understood that preserving information required more than just writing it down. It required engineering the very medium upon which it was written to be a partner in its own survival. To run a finger along those cool, sharp Sanskrit letters today is to touch a moment of dual intention, where a king's desire for glory met a craftsman's quiet promise of permanence, a vow written in iron that time itself has been forced to keep. Granite yields to nothing less than absolute determination. In the shadow of the step pyramid at Saqqara, Egypt, lies a subterranean labyrinth known as the Serapeum. Here, in long, silent galleries, rest dozens of colossal boxes, each carved from a single, solid block of rose or black granite, and each weighing between 60 and 100 tons. They are sarcophagi intended for the sacred Apis bulls, and their sheer mass is impressive enough. But it is when you lean close, when you run a light along the interior surface, that the true puzzle reveals itself. The inside corners of these boxes are sharp, perfect 90-degree angles, meeting with a precision that seems machined. The walls are flawlessly flat, polished to a mirror sheen. And then there are the holes, not random pits but clean, cylindrical drill holes, often found in the corners or on the lids, sometimes several inches deep. It is not the existence of the holes that confounds engineers, but the story told by the stone that was removed. In a few fortunate instances, the ancient workers left behind the evidence, the core samples themselves. These are solid cylinders of granite, drilled out and abandoned. To examine one of these cores is to witness a fossil of a machining process, running in a continuous, uniform spiral from one end of the cylinder to the other are deep, precise grooves. They are the unmistakable signature of a drill bit that fed into the granite with immense, consistent pressure and turned at a remarkably steady, rapid speed. The spacing of these spiral grooves is the critical clue. For a handheld drill, even one weighted down, to achieve such a uniform, deep cut in granite, the rotational speed would have to be very high to prevent the bit from simply grinding to a halt. A man with a bow drill using a copper tube and an abrasive sand slurry could theoretically drill granite, but the process would be agonizingly slow, and the resulting core would show erratic, uneven striations from the inevitable wobble and variation in pressure. The cores from the Serapeum show none of that. The grooves are even, parallel, and deep, suggesting a drill that was not only incredibly hard and sharp, but was also mounted in a stable, mechanical apparatus that provided both downward force and a smooth, fast rotation. This implies a level of tooling technology we do not traditionally associate with ancient Egypt. A copper tube, even with the hardest quartz sand abrasive, is relatively soft. Under the tremendous pressure needed to cut granite at the speed indicated by the grooves, a copper drill would deform, wear away rapidly, or simply snap. The consistency of the groove pattern suggests the drill bit itself was harder and more durable, perhaps made from a yet unknown alloy or even a different material entirely, and that it was being steadily fed into the stone by a mechanical, not a manual means. Some engineers who have studied these cores propose a mechanism akin to a lathe, where the granite block itself may have been rotated against a stationary cutting tool, a complete reversal of our standard assumptions. Others suggest a weighted, pulley-driven drill rig that could maintain constant pressure. The replication challenge is stark. Modern machinists using diamond-tipped coring drills can easily produce identical spiral grooves. But to do it with the tools listed in the standard archaeological record for ancient Egypt remains an unsolved problem. Experiments with reconstructed copper tube drills and sand abrasives can eventually drill a hole, but the resulting cores are rough, with irregular, shallow striations that look nothing like the clean, deep spirals from Saqqara. The difference is not one of outcome, but of efficiency and method. The Serapeum cores speak of a process that was controlled, powerful, and refined. They are silent witnesses to a workshop secret, a technique for persuading the hardest stone to surrender its form in perfect, helical curls. This evidence does not necessarily point to lost super science, but rather to a forgotten pinnacle of practical craft. It suggests that Egyptian artisans, through generations of innovation, may have developed mechanical aids and material treatments that elevated their work from admirable handiwork to something that still gives pause to modern engineers. These drill holes are more than just voids in granite. They are negative spaces that outline the shape of a lost technology, a ghost of a machine whose form we can only guess at, but whose work remains crisp and undeniable in the heart of the stone. The precision of a granite drill bit speaks to a culture's mastery of tools, but the Mycenaeans built to intimidate. At the entrance to their ancient citadel, a gateway stands not just as an opening, but as a declaration of power carved in stone. This is the Lion Gate, the sole surviving monumental sculpture from the Bronze Age Aegean world, and its construction is a lesson in raw, gravitational defiance. The gate itself is a classic example of post and lintel architecture, but executed on a scale that feels almost primal. The massive opening is framed by 4 colossal limestone blocks. 2 upright monoliths serve as the posts, each standing over 10 feet tall and weighing many tons. But the true feat of engineering rests directly above them, a single, staggering lintel stone. This block is estimated to weigh around 20 tons. To position this immense slab perfectly horizontally across the gap, creating a stable, load-bearing roof for the entrance, required more than just muscle. It demanded an acute understanding of balance and leverage. The builders likely constructed an enormous earthen ramp behind the gate, dragging the lintel up this slope until it hovered above the posts. Then, using levers and a system of ropes, they would have painstakingly inched it forward and lowered it into its final, precise position. a millimeter-perfect operation with zero room for error. The entire structure is a testament to what is known as Cyclopean masonry. The walls surrounding the gate are built from gigantic, irregular limestone boulders, fitted together without mortar. The name comes from the later Greeks who believed only the mythical Cyclopes, giant one-eyed beings, could have moved such stones. The blocks are not neatly carved rectangles like at Sacsayhuamán, but are rough-hewn, jagged polygons. The masons chose stones that would nestle together through their natural shapes, using smaller chinking stones to fill the gaps. This created a wall that was not only formidable but also remarkably flexible, able to settle and shift without collapsing during earthquakes, a pragmatic solution to a perennial problem. Yet, the true genius of the Lion Gate is not in its brute strength alone, but in the delicate relief carved onto a triangular slab of stone that sits above the lintel, designed to redistribute the immense weight of the wall above away from the opening. On this slab, two lionesses, now headless, stand in mirror opposition on either side of a single, sacred column. They rest their forepaws on altars, their bodies rendered with a tense, heraldic power. This sculpture is the crowning psychological element. To pass beneath this gate, you had to walk under the gaze of these guardian beasts, their missing heads once likely carved from a separate, gleaming material like bronze or obsidian, creating a fearsome, watchful presence. The engineering here served a dual purpose. The triangular relief is a brilliant structural solution, a corbelled arch in its earliest form, channeling the wall's crushing weight to the sturdy sides. But it also provided a monumental canvas, a billboard of royal and divine authority. The Mycenaeans combined sheer mass with symbolic artistry, building a threshold that was both an impenetrable barrier and a profound statement. The gate did not whisper of technical skill, it roared it. It communicated to any approaching visitor that the people within could command the very mountains, that they could lift the weight of the earth itself and carve their guardians into its skin. In its shadow, you understood that you were entering not just a city, but the domain of giants. The roar of a lion gate speaks of power concentrated, but a different kind of empire was built on the quiet, relentless flow of water. The Roman aqueducts were not just water channels, they were the literal lifeblood of an urban civilization, and their construction represents a foundational triumph of civil engineering that modern cities still rely upon in principle. To understand their genius, you must first forget the iconic, towering arches. Those arcades which stride across valleys like rows of stone giants are merely the most visible, dramatic sections. The true work of the aqueduct was invisible, a continuous, gentle slope carved through hills, buried in trenches, and tunneled through mountains, all calculated to an almost impossible precision. The entire system operated on one simple, non-negotiable principle: gravity. From a distant spring in the hills, the water had to flow downhill to the city, every single mile of the way. This sounds simple until you consider the reality of the ancient Italian landscape. The route was never a straight, smooth decline. It went over hills, across valleys, and through ridges. Roman engineers faced a monumental surveying challenge. They had to map a course of dozens, sometimes hundreds of miles, ensuring a consistent, shallow gradient the entire distance. The ideal slope was astonishingly slight, often a drop of only a few inches for every 100 feet of channel. Any steeper, and the water would rush too fast, eroding the channel walls. Any flatter, and the flow would stagnate or stop entirely. Achieving this required an artful dance with the land. When they encountered a hill, they didn't go over it, they went through it, digging tunnels that sometimes ran for miles. When they met a valley, they built those soaring arcades to maintain the vital, invisible downhill line. The precision involved is humbling. Using simple tools like the chorobates, a long, water-leveled surveying table, and the groma for sighting straight lines, teams of surveyors plotted these courses with an accuracy that modern lasers confirm. They were not just moving water, they were drafting a perfect line across a continent, a line that could not waver. The construction itself was a masterpiece of materials and forethought. The water channel, the Specus, was not an open ditch. It was a covered, waterproof conduit. The Romans lined it with a special hydraulic mortar, a cousin of their famous seawater concrete, and often sealed it with a smooth layer of waterproof plaster called opus signinum. This prevented leakage and kept the water clean. Maintenance was engineered into the design, with regular access shafts and settling tanks to remove silt. The scale of planning is almost incomprehensible. The Aqua Marcia, one of Rome's longest aqueducts, ran for 57 miles, yet its total drop from source to city was only about 300 feet. That means for nearly 60 miles the channel fell, on average, just over 5 feet per mile. To maintain that exact slope across such a distance, through all obstacles, is a feat of sustained geometric will. But the ultimate purpose was not technical display, it was urban transformation. This engineered water delivered up to hundreds of millions of gallons a day to a single city. It supplied public fountains, baths, latrines, and the homes of the wealthy. It flushed the streets and supplied water for industries. It made large-scale urban sanitation and public health possible for the first time in history, supporting a population density that would not be seen again in Europe for over 1,000 years. The aqueducts were the circulatory system of an empire, a network of stone veins that allowed the heart of Rome to beat. We still use gravity-fed water systems today, of course, but with pumps to assist and correct. The Roman achievement was to do it with pure, unaided gravity, to convince water to walk across a landscape at their command, through a stone path they built with a surveyor's eye and a mathematician's mind. They turned the fundamental force of nature into a public utility, proving that the highest engineering is often the one that works so perfectly, so silently, that we forget to wonder at the miracle of a simple, endless stream. These scattered wonders, from the self-healing concrete of Rome to the star-aligned streets of Teotihuacan, are not isolated curiosities. They are fragments of a larger, more profound story about human potential. What connects the drill core in an Egyptian sarcophagus to the iron pillar in Delhi, or the walking statues of Easter Island to the celestial gears of Antikythera? 3 powerful threads emerge, weaving through every feat we have explored. First, a mastery of materials that often feels like alchemy, whether it is the phosphorus-laced iron that heals itself or the volcanic ash mix that grows stronger with seawater. Second, a pursuit of precision that borders on obsession, from the hairline joints of Sacsayhuamán to the geometric perfection of the Costa Rican spheres. And third, a monumental ambition that defies pragmatic explanation, moving mountains of stone not for mere shelter, but to reach for the stars, to mirror the cosmos, or to honor beliefs we can only dimly perceive. This combination reveals a facet of ingenuity we sometimes overlook in our age of digital abstraction. It is an intelligence deeply embedded in the physical world, a knowledge won through the feel of a chisel, the tension of a rope, and the patience of observing a star's path for generations. The gap that captivates us is not merely a technological one. It is a gap in context, in mindset. We have the equations, but we have lost the intimate, hands-on dialogue with stone and metal that turned theory into timeless artifact. These creations challenge our narrative of linear progress, suggesting that peaks of understanding can be reached and then forgotten, that brilliance can be a fleeting spark in the long night of history. They ask us to remain humble before the past and endlessly curious. Each one is a conversation starter across the centuries, so we turn the question to you. Which of these 30 feats leaves you the most astonished? Is it the logistical miracle of the Bluestones, the cryptic genius of the Voynich Manuscript, or the quiet, flowing wisdom of the Minoan pipes? Share your choice and your reasoning. In discussing these echoes of lost genius, we keep the conversation alive, and we remind ourselves that the greatest mystery of antiquity is not how they built these wonders, but what our own era might one day leave behind as a puzzle for the future to solve.